In this video, we'll be going over section 9.1. We are dealing with systems of linear equations, and we're going to only be dealing with two variables in this section. So the first part is definitely a reminder of what a linear equation is. It's just an equation that's graph is a line. You can write as y equals mx plus b if you have two variables. We're also going to see three variables in the next section, so I'm just going to have an example of that as well. And then we'll talk about what a system of linear equations is. It's really just having more than one of them. Then the next part we'll talk about what it means as a graph when you have a solution of a system of equations. And this makes solving systems of equations very nice, and in general, systems of equations are very hard to solve, but if they are linear, it's pretty easy. The two methods that we will introduce in this section for solving them are substitution and elimination. You may very well be familiar with the substitution when we get there. You may also be familiar with elimination. But you'll notice when we get there, I'll stress doing elimination method, because in this chapter, the back half of this chapter, we will be dealing with matrices, and the way matrices work in solving these is with elimination. They do not use substitution. And then the last thing is just doing a word problem related to this stuff. They'll also be the kind of word problems you're familiar with when we get there. All right, but a lot of little things in the background of this section. What a linear equation is. A linear equation is any equation in which the only powers of any present variables is 1. And I have an example here, a linear equation with two variables, something like having an x and a y, but with no powers. And it's called an equation because we have an equal sign. The 2x plus 3y equals 7 is an example of a linear equation with two variables. A linear equation with three variables, typically we use the variables x, y, and z. And same idea, no powers except 1, and it's an equation. We have like x minus y plus 4z equals 1. Now, one of the things you'll notice, the way I wrote these equations is having the number on its side, on the side by itself, and then the x and y stuff in alphabetical order, which that part's optional, but on the left side. And this is something you should have seen before. It's called standard form. You don't necessarily need to remember that specifically or anything special about standard form, except it has this setup. And when we do almost anything with linear equations, systems of linear equations, we need to be in standard form. And you'll see that in the problems we do. Now, the next part is just defining what a system of linear equations is. And a system of linear equations is a collection, so more than one, of linear equations. A solution of a system of linear equations are all the coordinates that make every equation true. All right, so example right here, this is a system of linear equations. We have 1x minus 2y equals 16. And another one, negative 2x minus y equals 8. All right, this is just an example. I'm not actually solving this or going to do anything necessarily with it. But this is an example. One thing I want to point out here is some terminology. We will say this is a 2x2 system to avoid confusion, because it doesn't tell you which two is which. The number of equations comes first, and then the number of variables comes second. All right, this is, once again, this is going to be one of these things when we talk about matrices. Everything lines up with our systems of equations. We will have only 2x2 and 3x3 systems in the next section. When the numbers are different, certainly those are things you can solve, but it gets a lot more general as far as solving them, and that's not a topic for this class. But the number of equations comes first, the number of variables comes second. 2 by 2 system, I'll typically write it like this. I will say 2 by 2, but I'll write it'll look like 2 times 2 written down. All right, in this example, a solution to this system of equations is x equals 0 and y equals -8. Once again, we're not really doing anything specific here. I'm just telling you this is a solution. The reason we know it's a solution is if you plug in x equals 0 and y equals -8, then it solves both equations. So if we plugged in x equals 0 and y equals -8 in the first one, you could see we get 16. And if you want to write it out, you can. And the second one, if you plug in x equals 0 and y equals -8, you also get 8 here. It has to work in both. It can't just work in one. And that's very important. Okay. Now, typically, the way you would start this, solving these systems of equations, is by graphing, because you learn how to graph these things. A solution would be where their graphs intersect. But we're not going to deal with equations that only have intersecting lines in this class. So what I want to do next, what you'll see is a little chart. There are 3 kind of solution types, you could say, to a system of equations, 2 by 2 linear equations. I'm going to scroll down and go to that. All right, so a graphical interpretation of a solution. Trying to get it all on the same page. All right, the linear systems are heavily studied in higher mathematics. If you end up doing a math major or math heavy major, like a lot of the sciences are, engineering, one of the tools you use a lot is something called linear algebra, which is basically studying linear equations, systems of linear equations, but there's a whole class for it. And you want to know what are the solutions to this linear equation, system of linear equations? What's the best solution, if that's a relevant question for you? And we don't ask that second question in this course, but ultimately what you're doing is you're trying to find where the lines intersect. For a 2 by 2 system, it's where do the 2 lines intersect, and we have these 3 possibilities. Right. So one possibility here, which is the one that is most common, is if lines aren't parallel, then there's one solution. Okay. So the way to kind of quantify this left picture, the lines are not parallel. And there is one solution. Now, when we solve it algebraically, you don't necessarily need to recognize that they're not parallel to do it. You're going to do the same thing no matter what. But if you get one solution, that means the lines were not parallel. Now, if the lines are parallel, there are 2 possibilities, which you see in the middle and on the right. You have parallel but not touching, and parallel but are touching, which means they're the same line. Most people as far as this right picture goes, think of just the same line and not parallel, but to really establish why this is all of our possibilities, either lines are not parallel or they are. If they're not parallel, they always intersect. If they are parallel, they either never intersect because they're not the same line, or they intersect everywhere. So we got parallel and not touching. And in these 2 examples here, you can see if they're not touching, that means there's no solution because they never intersect. If they're parallel and they are touching, then you have infinitely many solutions. This is really the example in the higher math classes, linear algebra, that you study, because most things are going to have infinitely many solutions. You have to find what we would call the best one. All right, but one thing I want to point out here, you'll see in some problems that when you have infinitely many solutions, sometimes you're asked, give me a couple of them. I want a couple of the solutions. And we can actually figure those out based on the work we do. But we can get the solutions as an equation, as equations for this one. Once again, we will see that. I'm just bringing it up now. No solutions, straight up. There's no solutions. There's nothing to say other than no solutions, or D and E if that's what the homework wants you to say. And in one solution will be the thing you're used to. But you'll see the technique, what we'll get as we solve the problems. Right? But this is all the possibilities. There is not a possibility of two solutions. Yeah, so this example over here, when you get one solution, you get an X and Y pair. You do get an X value with a Y value, but we say that is one solution. The other thing I want to point out about this chart, you might see some of this on the homework. It might ask you whether the system is consistent, if it's independent, if it's dependent, if it's inconsistent. Consistent means there's at least one solution. So the one on the left and the right are both consistent. Independent means there's one. Think about independent being alone. There's one solution. Dependent means you depend on other things. So that's when there's infinitely many solutions. And inconsistent means there are no solutions. Right, but those are some words that you might see pop up on the homework. Just be aware of that. And this is just me describing what we just talked about. Right, so when we go through and solve these things, you will get either 1, 0, or infinitely many solutions. Algebraically, I just wanted to outline this before we go through. If you get an actual X and Y value, you get a number for X, you get a number for Y, then there is one solution. That's how you can know. And that's probably what you're most used to. When you do word problems as well, this is what you usually get, because there's almost always one solution to a word problem. The second point, if you get a contradiction, which means you get two numbers that don't equal each other, like 0 equals 1, 4 equals 12, -7 equals pi, you know, just any two numbers that don't actually equal each other, then there are no solutions. And then the third example, when you get infinitely many solutions, it happens when something is always true. For example, if you get 0 equals 0, that's always true. It could be 1 equals 1, it can be pi equals pi, 4 equals 4. As long as we get the same number, there are infinitely many solutions. This is pretty much a general truth, no matter what the size of the system of equations are. But we will see in the next section, it's possible to get both of these at the same time. But we'll talk about that more specifically when we get there. All right, so now we're just going to actually solve these things. And, you know, like I said at the beginning, you're probably very aware of how to do at least substitution. But as I have outlined here, the common methods are called substitution or elimination. The common thing that we're going to do in the later part of this section is with matrices, they mimic elimination methods. So I highly recommend you practice and understand that. But I will do one example with substitution just as a refresher. It is nice to remember how to do that. And another point that I'll mention here is when you do elimination, it's a lot easier to tell if there are 0 or infinitely many solutions, because your equations will look pretty much the same. But that, once again, we'll see that as we go through. All right, so solve the system by substitution. I just have the method outlined here. What you do in substitution method is you solve for a variable in one equation and plug it into the other equation. So this one's really set up for us. This system of equation is set up for substitution because this is solved for y. The second equation is solved for y. And if you are given this problem on the homework or the test or something without being told this, you would want to use substitution because it's solved for a variable already. So it's solved for y, and we take, really that first part is done for us. It's solved for a variable in one equation, and we want to plug it into the other. So we plug in for y in the other equation. Now, I have seen this mistake a couple times with substitution, which is also something that doesn't pop up with elimination. If you solve for a variable in an equation, you can never plug it back into that same equation because it will always give you 0 equals 0. You must plug it into the other equation. All right, so I'm going to go ahead and do that. In place of y in this first equation, I'm going to put 4x plus 22. We get 3x plus 2. Y is 4x plus 22 equals negative 33. And you see the point here with this substitution method and all of our methods is to make an equation with one variable, because we can solve this. Now we have just x in here. We can distribute the 2 through. We got 3x plus 8x plus 44 equals negative 33. Continue solving. Subtract the 44 from each side to get the x's by itself. Combine them. 3x plus 8x is 11x. We got 11x equals negative 33 minus 44 is negative 77. And we divide each side by 11. And we got x, which is negative 7. All right, so right here, because I got an x value, I'm going to know there's one solution. That's one way to really indicate that. If you get an x value, you'll be able to get a y value. But you're not done. You still need y. And we need to get x with a y. So don't accidentally stop here because you've only done half of the solution. But what you do here is you take your x value and you plug it into either equation, and you can solve for y. The reason you can do either equation is because the solution has to work for both. It's much easier to plug it in the second one in this example here because it's already solved for y. So I plug it into either to get y. And I'm going to plug it into the second one. Like I said, we get y equals 4 times x, which is negative 7, plus 22. 4 times negative 7 is negative 28. Plus 22, which equals negative 6. Right, so x is negative 7 and y is negative 6 makes up our answer. Just depending how the homework wants you to answer it, you can there might be a spot for where x goes, there might be a spot for where y goes, or they might want a coordinate pair. If they want a coordinate pair, we do x comma y, negative 7 comma negative 6. Okay, so that is our answer. But once again, there's one solution. It is this. If you graph these lines, it will intersect at this point, and that's all. But you have to get the x with the y. And I'll just go ahead and indicate this means there's one solution. All right, substitution method also, as far as doing it compared to elimination, when you have one solution, it ends up being about the same amount of work, and it's just as straightforward to see. Elimination method really benefits when you have zero or infinitely many solutions, and if if you're solving a problem, you're not going to know that at the beginning. So that's something to keep in mind. Another reason why you're going to want to practice elimination method. All right, so the first one here under elimination method, our system of equations, we want to solve negative 6x minus 4y equals 10 and negative 9x minus 6y equals 12. All right, so the idea with solving systems by elimination is to eliminate a variable. That's why it's called that. And to eliminate a variable, the things you can do, you can add or subtract equations. So we can just add these together, we can subtract them. But what you're almost always going to have to do first is multiply or divide equations by numbers to make them match. All right, so what I mean is, let's say for this first one, I want to eliminate x. Unless if there's clearly a better one out of the x and y, maybe if you just added them together, you would see that one would eliminate directly. I always just eliminate x. Okay, try to keep it standard as far as doing the problem. If we want to eliminate x, what we want to do is make the numbers on x in both equations match, for lack of a better term. That way, if we add or subtract them, we'll get 0. Okay, so we want to make the coefficients on x match. I'm going to put that in quotes. The reason I want to put that in quotes is, I actually prefer if they match, but one's negative and one's positive, like -3 and +3. And the reason why I like that is when they're off by that negative sign, when you add the equations, which is a lot easier for me, I won't forget that minus with subtracting. That's what makes them go away. And so, like I said, we'll make the coefficients on x match, and the idea behind that is by multiplying or dividing our equations by numbers to do that. All right, one thing you do not want to do, you do not want to multiply or divide the equations themselves. That will not help you. It will not lead you in a good path. Right. So the thing I typically look for to do this, there's one thing that always works. If you multiply one of the equations by the other opposite coefficient, meaning if I multiply equation 1 by 9 and equation 2 by 6, that'll work. And if you want to make them miss a negative sign, you can do one negative. But it is a good idea, if you see something in common, to factor it out of your equation, and that just makes the numbers a little bit smaller and easier to work with. Right, and what I see with equation 1 is there's a 2 in common, and equation 3 there is a 3 in common. I'm going to divide equation 1 by 2. Equation 1, I'm just referencing the top one. And I'm going to divide equation 2 by, I'm going to make it -3 instead of 3. Because I want that opposite thing. I want the numbers on x to be the same value, but have opposite signs. So same absolute value. But if you do it this way and you divide equation 2 by 3, your end result will be the same. You'll just have one slightly different step. Okay, so if I divide equation 1 by 2, I'm just dividing all the coefficients by 2. I get negative 3x minus 2y equals 5. And if I divide equation 2 by negative 3, then I get 3x plus 2y equals negative 4. Right, now don't worry at this step about, well, I think, if I add these, more is going to eliminate than I want. Your goal is to eliminate x. Wow, that's not how I spell eliminate, and I didn't realize it. Eliminate. Your goal is to eliminate a variable. If more eliminate with it, that's fine. Right, but what I was talking about with the opposite thing is now if we add these equations together, okay, what you're allowed to do. If you don't do the opposite thing, then you'll have a negative 3x here and you would subtract them. And you want to be really careful when you subtract to not forget a minus sign. What you'll see here, it's negative 3x plus 3x goes away. It would be like 0x, which normally I wouldn't write in. We're also seeing that negative 2y and plus 2y also go away. We get plus 0y. And 5 plus negative 4 equals 1. Right, so we added our two equations and we got this thing. Once again, normally you don't write 0x, 0y because it's just 0. So this side over here, the left side is just 0. And the right side equals 1. And if you recall what happens here, if you get a contradiction, if you get one side as a number, both sides are a number rather, and they're different, then there is no solutions. And you stop there. If there are no solutions, you're done. So there are absolutely no solutions to this. There's nothing more to do. And what I was saying before about elimination and substitution being easier, elimination being easier than substitution when you have things like this. If you try to do substitution for this one, which means if you try to solve for y or x in one of your variables or equations and plug it into the other one, you're going to get a whole bunch of messy fractions. If your fractions, if you simplify even one of your fractions incorrectly, you will not get 0 equals 0 or 0 equals 1 or something like that, and you'll end up with the wrong answer. So it's better to do elimination. You can always avoid fractions till the very end with elimination. All right, but we'll do one more here. So here we got 4x plus 8y equals 16, and negative 6x minus 12y equals negative 24. And I'm going to do elimination, and I'm going to start with the same idea. It's not obvious to me that eliminating x or y would be easier because we can't just simply add or subtract. So I'm going to eliminate x. And I'm going to do this one the other way for eliminating x, even though I see there's some stuff in common that I could factor out. I'm going to intentionally do the multiplication by the other thing to eliminate x, meaning I'm going to multiply the equation 1 by 6, the opposite, and I'm going to multiply equation 2 by 4, the opposite. That's not how you spell multiply. Okay, so if you see stuff in common to divide out, definitely you're welcome to do that. I'm just showing the other way. We're going to multiply equation 1 by 6, and when we do that we get 24x plus 48y equals 16 times 6 is 96. And like I said, I want to multiply equation 2 by the coefficient up here, 4. They're already opposite sign. So I don't have to worry about multiplying by a negative to make that work. If we multiply equation 2 by 4, we get negative 24x minus 48y equals 4 times negative 24 is negative 96. All right, the x coefficients are matching but opposite, so we add them together. Add the two equations together. The x, the 24x and the negative 24x go away. The 48y and the negative 48y also go away. And on the right side, 96 and negative 96 also cancel out. We get 0 equals 0. Everything eliminated. But you don't want to leave it blank. You need to write 0 equals 0. And in this case, remember when we get a number on each side and they are the same number, there are infinitely many solutions. Okay. And once again, you may have gotten to this part right here when I wrote that down and realized, well, these are actually going to be exactly the same, and I'm going to get everything that cancels out. So once again, that's the benefit of elimination method, is you can see it much quicker than substitution. Right, but that is an example of each. Certainly, elimination method, if you do it, you can get one solution. You could have done elimination method on this one. You would have gotten the same answer. You could have done substitution method on these two and gotten the same answer. But like I said, you really want to practice elimination method first. All right, so just have one application here. There are plenty of word problems we could talk about. Anytime you have a few things, one of the classic ones is like, I have a bag of nickels and dimes, and I know I have 78 coins and they add up to $4.20 or something. How many nickels and dimes do I have? Yeah, that's kind of the kind of word problem you would see. But I wanted to do something that would be maybe more related to something you would do in school, which is in a chemistry lab like this. Right, so it says you need a 45% alcohol solution. This is what we need. Keep that in mind. And on hand, you have 550 milliliters of a 35% alcohol mixture. So we're told one thing. We have an alcohol mixture that has 550 milliliters. And you also have 95% alcohol mixture. And I'm guessing the way the problem's set up, they're saying you have as much 95% alcohol mixture as you need. The question is, how much of the 95% mixture will you need to add? And they're saying, well, you need to add to this 35% mixture, 550 milliliters, to get the desired solution. Right, so the idea with any word problem is to define, like this, is to define your variables. We need to know how much of the 95% mixture to get our desired result. So the good idea would be calling X something like the amount of the 95% mixture. Now, a lot of questions like this, you might not actually be told how much of the 35% you have. Maybe you are told by your lab professor to add a certain amount and then figure out how much of the other one to add, which is like this one. So typically we would say Y is the amount of the 35% mixture, but we just happen to be told that it's 550. X is what we're searching for. We want to solve for X when we make our equations. Y would be our helper. And what we need is a 45% mixture. Right, so the idea of the equation is this. Making an equation. You have an alcohol. Since we're dealing with an alcohol solution, you have an alcohol equation. And what that's going to tell you is the amount of alcohol that's in your final solution. Meaning the amount of the 35% solution that's alcohol. Right? It's going to be 35% of 550. Then you don't need to figure that out right away. Just do 0.35, that's our 35%, times 550. Right, this is the amount of alcohol in the 35% mixture. Right, I just switched 35 to 0.35 and the amount that we're adding. And then I would want to also put in the amount of alcohol for the 95% mixture. Now we know that's 95%, but we don't know how much we're adding to it. So that's what we called X for. Right, so once again, we have the amount. We have the percentage is 35 times the amount. The percentage 95 times the amount, which is unknown. And what you want to think about here, what does this need to equal? Well, we need it to be a 45% solution. So we need a 45% solution. The right side of this equation is going to be what we need. And the amount in the 45% solution, you don't know what that is, but it's going to be 550 plus X. It's going to be the amount of X you add to that 550. All right, so I'm going to rewrite that equation to make it more clear. But once again, this is the amount of alcohol in the 35%. This is the amount of alcohol in the 95%. If you add them together, that needs to be the amount of alcohol in the 45% final solution. So we got 0.35 times 550, just rewriting it, plus 0.95 times X equals 0.45 times 550 plus X. Okay, all right, so that is the amount of alcohol equation. What you want to realize here is that you're trying to solve for X and it is your only variable. The reason it worked out like that is because they told us what Y was. Right? If this was Y, then you would have a Y over here. Right? But they would also have to tell you then what the final amount is. So everything works out. You're not going to be not given enough information. And I spelled alcohol wrong. Good thing this is not an English class. All right, but now we can solve for X, which is what we're trying to do. We made our equation with the variable X for a reason. So go ahead and distribute on the left side and multiply the 0.35 times 550. 0.35 times 550 is 192.5 plus 0.95x. If we distribute the 0.45 through to the 550, we get 247.5. And then we distribute the 0.45 to the x, and that's exactly what that is. All right, and now we can just solve this like we normally would. Gather the x's on one side and the numbers on the other. put the x's on the left, subtract the 0.45x. And then subtract the 192.5 to the other side. That cancels out, that cancels out. 0.95x minus 0.45x is 0.50x. Or you can just leave 0.5. And then 247.5 minus 192.5. Let's just make sure that we don't mess that up. Since we've done all this work at this point, we got 55. And then divide by the 0.5 to get x. And if you do that out, 55 divided by 0.5, that's a half. So 55 divided by a half is 110. Right, so what we figured out is we need to add 110 milliliters of the 95% solution to get our final to 45%. Right, so remember also that is what we were solving for. That's how we made our equations. And this kind of makes sense if just because, 35 is a lot closer to 45 than 95 is, we should probably use a lot more of the 35 than the 95 in this. Right, but this is systems of equations with two variables.